everyone, today we are going to start Chapter 5 by talking about operations with polynomials. There are a few objectives in our to-do list for today. We are going to first work with factoring when we have a sum or a difference of two cubic polynomials, meaning that there's an x to the third power. We are also going to identify leading coefficients, degrees, and constants in a polynomial. We're going to look at a polynomial or look at a function and decide whether or not it is a polynomial, and we're going to then add, subtract, and multiply polynomials. So let's get started. The first thing that you need to know is this pattern or this formula for factoring whenever you have a sum or difference of two cubes. So notice here that in this formula here, you have some number, some base raised to the third power plus or minus some base raised also to the third power. The rule is going to say that when you need to factor these, the first factor, the first set of parentheses, is going to be these two bases with the same sign. So this is the two bases added together, whereas in this other difference, it's the two bases subtracted. The second factor is going to have three terms in it. Notice that the first term and the last term here are both of the original bases, the first base and the last base. This time, though, the first base is squared and the second base is squared. The middle term is when you multiply together the two bases. The signs for these, you're going to use the acronym SOAP to follow, meaning that the same sign is used in the first factor, and then these two signs in the second factor are going to be the opposite sign, that's what the O stands for, and then the last one is always positive. This is going to be true whether you have a sum or a difference of two perfect cubes. So let's look at some actual examples because that was pretty abstract what we just talked about there. So let's look at x to the third plus 2 to the third. Both of these are cubes and they're being added together, so that's a sum. So that means we can factor this by using this SOAP method. So I'm going to draw my two sets of parentheses. The one on the right is going to be a little bit longer because it's going to have three terms in it. The first one on the left is going to have my two bases, x and 2, and according to SOAP, I'm going to use the same sign as the original problem. It has a plus sign, so I'm going to put a plus sign. Now the second factor, this is the trinomial here. So whatever my first base is, I'm going to put that in the first spot and square it. Whatever my second base is, I'm going to put it in the last spot and square it. Notice that I took my base 2 and I squared it because that's what the formula told me to do. And then this middle term is going to be my two bases multiplied together, x times 2 or 2x. Now to determine my signs, I'm going to use SOAP. So my first one I've already done is the same. The second is the opposite, so because this is an addition problem, I'm going to put a subtraction sign there. And then the last sign is always positive. So then this is the fully factored version of this cube, or this sum of cubes. So let's do another one to get that pattern again. I have two bases, both are cubics, and we are subtracting this time. So let's draw our two sets of parentheses. The first factor is going to have the two bases with the same sign, so that's x minus 2. The second factor is going to have the first base squared in the first part, the last base squared in the last part, and the middle is going to be the 2 multiplied with the x. The signs are going to be same, opposite, always positive. Now I want you to look at both of these. There is a simplification that needs to happen. Do you see what it is? Do you see this 2 squared? I need to simplify this. So in both of these, I'm going to write x plus 2, x squared minus 2x plus 4. And in this one, I'm going to write x minus 2 times x squared minus plus 2x plus 4. So notice here that you may need to do a little bit of simplifying depending on what the problem is that you're factoring. I also want to point out too that you need to be sure to square all of the base. So if one of these bases had been like 2x and the quantity was raised to the third power, the base is 2x here. So that means when I do this part here and I square it, I'm doing 2 squared and x squared. Be very careful with that you're squaring the entire base, not just part of it. Now, anytime you use the SOAP method to factor cubes, you can always FOIL them or distribute them back together to see if you get the original problem. So let's do that with this formula, this a minus b times a squared plus ab plus b squared. So let's do some distributing on steroids, basically. All right, so we're going to do a times a squared, which gives us a to the third power. Then we're going to do a times ab, which is positive a squared b, because there are two a's being multiplied together. A times b squared gives us a b squared. Now we need to do the second term. I'm going to change my color here just so it looks a little bit more clear. This time I've got negative b, so I'm doing negative b times a squared, which is negative a squared b, negative b times ab, which is negative a b squared, because you've got b times b, and then this last part is negative b times b squared, which is negative b to the third, because three b's are multiplied together there. All right, so now I know this looks kind of ugly, but look at the middle terms in this expression. Do you see this a squared times b, and also this minus a squared times b? Those are going to disappear. Look at this one, a times b squared minus a times b squared. When you combine these like terms, they equal 0. So that leaves us then with a to the third minus b to the third. And that was the original problem up here that we used this pattern with. This will work with any set of numbers. If you correctly factor a sum or difference of two cubes, you can always distribute them back together, your factors, and you should get the original problem that you started with. All right, so let's look now, if I can get this to advance, there it goes, at the cubes you're expected to know, and then do some practice with this. Do you remember the cubes that you're supposed to know? 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, and 7 cubed? These were all on that sheet of perfect numbers that I asked for you to memorize back in chapter 4. So let's go through these and make sure you've got them. 1 raised to any power is just 1. 2 cubed is going to be 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. And 7 cubed is 343. These you have got to know, and we're going to see why here in a moment when we do some practice problems. You have to recognize that these numbers are cubes. So if our directions say to factor each expression completely, let's see what we can factor. Still looking for a GCF first. This first problem doesn't have a GCF, so I'm not going to take out a GCF, but I do see a perfect number. I see this 8. So if I rewrite this as x to the third plus 2 to the third, because 2 to the third is equal to 8, this now is just like the sum of 2 cubes, which we just learned the SOAP method for. So we're going to factor this by applying that SOAP method. I'm going to draw my two sets of parentheses. The first one is going to be the two bases with the same sign, so that's x plus 2, these two bases with the same sign. My next set of parentheses, the first term is going to be my first one squared. My last term is going to be the second base, 2 squared. And my middle term is going to be the bases multiplied together, so that's 2x as my middle term. Now to do my signs, I have same sign, opposite sign, and then always positive. So that is my, oops, fully factored, but I do need to change this 2 squared. I'm just going to erase it there and write a 4. You could write that out as a second step if you'd like, or a third step if you'd like. This does not factor anymore, so I'm done. Let's try another one. This one has a GCF. Do you see that both of these are even numbers? That means I can take out a GCF of 2. It leaves me with x to the third plus 125. 125 is one of your cubes, so that means we can use the SOAP method to factor. We can write x to the third plus 5 to the third, and then factor that set of parentheses. So I'm going to leave my 2 out front and write my 2 sets of parentheses for my other factors. I'm going to use the same basis with the same sign for my first factor, so that's x plus 5. I'm going to put an x squared in my first spot for my second set of parentheses. The 5 squared is going to go in my last spot. I'm going to write that as a 25 here. The middle is going to be the 2 bases multiplied together, so that's 5x. And now I can do my signs. I have same, opposite, which is a minus, and then always positive. Okay, now this one we are not quite done with yet. And that's because this trinomial, this last factor, it factors more. So we still, oh wait, no it doesn't. I take that back, silly me. This is fully factored here. So we're done with that one because this piece does not factor anymore. That is something that I would like for you to be very careful as you move forward. Be sure to look at this trinomial, make sure it doesn't factor anymore. Alright, so let's talk about polynomials themselves a little bit because I've thrown the word around quite a bit. A polynomial function is a function of the form f of x is equal to a sub n times x to the n power plus all of these smaller orders all the way down to the constant term, a to the 0. All of the coefficients, meaning these numbers that are out front of the x, they all have to be real numbers. And all exponents for the variables with all these x's have to be whole numbers. That's going to help us and be very important in a moment. And the first term, of course, this a sub n, it has to be a number that's not 0, because if it's 0, that term disappears, and that's not good because then we don't have a polynomial anymore. Okay, so a sub n, this number that's out in the very front of the x to the biggest power, that is called our leading coefficient. The n, that's the exponent with the x, is called the degree of the polynomial. You might also hear the word order. And a sub 0, which is this last term over here, that's our constant term. It's the one that does not have a variable with it. Okay, so when we have a polynomial function, it's in standard term if everything's written in order. And what I mean by in order is that the exponents are in descending order. They start on the left with the biggest, and down on the right is the one that doesn't have an exponent or a variable at all. So if you look at this example, f of x is equal to 2x cubed minus 5x squared minus 4x plus 7. Notice that the biggest exponent, 3, is on the furthest left, and then it goes 2, 1, and then x to the 0 power. So this one is in standard form. We can name the leading coefficient by looking out in the very front. The x with the largest power, the degree, whatever that value is, that's our leading coefficient. The constant, remember, is the term at the end that does not have a variable with it, so it's 7. And the degree is that highest power, so the degree is 3 here. Now let's look at how we can determine if something is a polynomial or not. So there are many different types of polynomial functions. I've given you a list here of the name of each depending on the degree. So if you have an x to the 0 power, that means you don't have an x, so it's just a constant number. If you have an x to the first power, you call that a linear function. A quadratic, that's what we just studied in the last chapter, that's an x to the second power. The degree of a cubic is 3, meaning it's to the third power, and a quartic is a degree 4, so that means it's to the fourth power. I also want to add on to this list that a fifth degree polynomial is known as a quintic. So with that, now let's work on identifying some polynomials and naming them. Remember that I said a moment ago that there were those two important things in the definition? All coefficients must be real numbers and all exponents of variables must be whole numbers. Those are the two questions we're going to ask ourselves to decide if an equation is indeed a polynomial function. So let's look at some examples. In this first one, g of x is equal to negative 4x squared minus 8x to the fifth plus x to the fourth. Now this one is not in order, but if we just look at all of the terms, are the exponents whole numbers? We have a 2, a 5, and a 4. So yes, they are. Are the coefficients real numbers? Negative 4, negative 8, and 1. Because the answer to both of those questions is yes, we can say yes, this is a polynomial. So let's complete this row of the chart for this polynomial. First, we need to put it in standard form. So we need to write it so that the leading coefficient and the degree are the first term. So I'm going to write that g of x is equal to negative 8x to the fifth, because this term has the highest exponent. And then I'm going to go in descending order after that. So I see this 4, that exponent, that's a 4, so I'm going to put that next. And then the lowest one is this x squared. So minus 4x squared is the last piece. Remember, the degree is the largest exponent, so the degree is 5. Because the degree is 5, that means our type, our name, is quintic. And the leading coefficient is the coefficient with the highest degree, so that's negative 8 as our leading coefficient. Let's look at a couple more determining whether or not these are polynomials. H of x says, let's see, 6x to the 1/2 minus 5x. Are the exponents whole numbers in this one? The answer to that is no, because there's this exponent that's a 1/2. So this one's automatically not a polynomial. We don't have to do the rest of that row because it's not a polynomial. F of x is equal to 2 raised to the x power. Are the exponents whole numbers? We don't know in this one because we have a variable for the exponent. So no, this is not a polynomial function, and we don't need to do the rest of that row because it's not a polynomial. And then this one is 3x raised to the first power. Are those exponents whole numbers? No, whole numbers are numbers that are not negative here. So negative 1 does not work. This one is not a polynomial, and I don't have to do that one either. So be sure that when you are looking at something and you look at whether or not it's a polynomial, look at the exponent, see if it's a whole number, and look at the coefficients, make sure they're real numbers, no i's in them. Okay, let's move on to the last piece, which is the actual operations with these polynomials. We're going to add, subtract, and multiply. Adding and subtracting is going to be very similar with what we were doing with quadratics before, and really multiplying to some degree is too. So notice that there are these two factors, but they are being added together, these two expressions. So we are going to find the like terms and combine them. So this one has an x squared term, so I'm going to look over here and go, okay, that has an x squared as well. So I'm going to add those two numbers together because it's asking me to add. 2 plus 4 is 6x squared. And then I have this minus 8. My like term is this one that's also a constant. So I'm going to do negative 8 plus 4. That's negative 4. And then these guys don't have any buddies with them, any other like terms to combine. So I'm just going to write them as they are. Plus x to the third minus 12x. After I get here, I want to rewrite this in standard form. So this x to the third, that's my highest exponent, so I'm going to write that in the front, and then I'm going to go in descending order. So plus 6x squared minus 12x to the first power minus 4, the constant term. And that is my final answer there. With subtraction, we're going to take subtraction and turn it into an adding problem by distributing the negatives. So this negative we're going to distribute to all of these values in the second term, which means that's going to be a plus. When we distribute it, those become minus, that one's a plus, and that one's a minus. Now this is exactly like the addition problem we just did. You have 2x squared. We're looking for a like term. This negative 4x squared works, so that's negative 2x squared. Then you have this negative 8. So we're going to add that to the like term of negative 4, which gives us negative 12. And then we're just going to list our other terms that don't have anything to combine it with. So negative x to the third plus 12x. I again need to work on getting this one into standard form. So I'm going to put that negative x to the third first, then minus 2x squared plus 12x minus 12. And that is my final answer in standard form. Okay, so the last thing we need to do is multiplying polynomials. Look and see this quantity is being squared. Do not distribute that square inside. You cannot do that distribution because this is a binomial. There are two terms in the quantity that's being squared. Instead, what this means is that we have 3x squared plus 7 times 3x squared plus 7. So we need to apply the distributive property here. That means that we're going to do some multiplying. We're going to multiply these first two, distributing there. 3 times 3 is 9. X squared times x squared is x to the fourth. Then we're going to distribute that 3x squared to the 7. 3 times 7 is 21. Got that x squared that we don't want to forget about. Then we're going to distribute the 7 over into the second term. So we're going to take the 7, do 7 times 3 is 21, x squared, and 7 times 7 is 49. Now I do need to combine some like terms here. I have these two like terms. So let's see, we have 9x to the fourth plus 42x squared, and then there's that plus 49 constant on the end. So that is fully multiplied and it's in standard form, so I don't need to do much more with it. Okay, so in this video we factored using that SOAP method for the signs when we have a sum or a difference of cubic polynomials. We also looked at how to identify the leading coefficient, degree, and the constant term. We looked at how to determine whether or not a polynomial or a function was a polynomial, and then we did some adding, subtracting, and multiplying with polynomials. You have a couple of problems on your note sheet now that I'd like for you to go ahead and try.